So then I have to watch out for this.
Yes, be careful.
Yeah, we'll do that for you.
All right, it's my great pleasure to introduce Refik Soyer as our joint statistics and SEOR seminar speaker. Refik is from GW, from business school. He's a professor in decision science and statistics there. He's a GW graduate as well, and Refik works on developing Bayesian methodologies, and his work is mostly driven by applications in reliability and queuing theory, and objects is working with a lot of time series, and today we're talking about multivariate discrete time series and Bayesian methodologies to analyze those type of data sets. Please welcome.
Yeah, well, thank you, Vadim. We have had a lot of good connections with, I guess, George Mason, for example. I think Ariella Sofer was my office mate, so we go a long time, and a lot of friends in the audience. And I guess Ran is also in the department, so we have good connections. So it's good to be here, especially on a nice day like this. Also, the markets are up, so things look better.
When did it go up? I didn't check. This morning.
This morning, yeah. Well, hopefully it will stay. Well, I don't know whether you guys know about Nick Poisson, my co-author, but he's big on markets. He's my financial advisor, so I always talk to him. I know nothing about the markets. Okay, so this is joint work with Tevfik Aktekin at University of New Hampshire and Nick Poisson, University of Chicago. So this is just the outline. So we'll basically focus on discrete time series of counts, and with an emphasis on the counts like Poisson type of counts, as you will see, and talk about how do you model temporal as well as the component correlations, and then talk about different type of strategies, going back to Cox's general framework of observation-driven and parameter-driven type of time series models, talk about state space and using random environment to induce some type of correlation, then talk about basically Bayesian inference, both MCMC and particle filtering for real-time updating. I'll show some real illustrations, and then talk about the extension to other type of time, non-Gaussian type of time series. And all the details of this talk is on this article which just appeared in the Bayesian analysis. So there are more studies and all that numerical illustrations over there. So the discrete valued time series arise in a lot of different applications. For example, there is a nice review paper in the International Statistical Review by Schmidt and Pereira, 2011. There are applications in ecology, abundance of organisms. There is a nice paper by Ravi Shankar and her authors in the statistical interface. And there are a lot of business type of applications. For example, we did some work in mortgage defaults, call center arrivals, and then household shopping trips, and I'll talk some of those. And there is a recent volume on the discrete valued time series, which just came up like 2-3 years ago, which was, I think, edited by Nalini Ravishankar, David Scott, and I think Scott Holland, if I'm not mistaken. And there are also some other, like on crash counts, internet traffic. Mike West and his colleagues basically has a very nice paper in 2016, JASA. And when you deal with discrete valued time series, obviously you have to bring in the correlation, and there are different type of ways of doing it. You can either have it on the observations or on the parameters. But then when you go from the univariate to multivariate time series, you have to also talk about how to induce correlations on the components, right? Contemporarily, contemporary type of correlations. And when we think about multivariate time series, probably we are mostly comfortable with Gaussian type of framework, because there is a natural way of inducing correlation. So that's why there is a lot of work on vector AR processes, in the Gaussian type of framework. So when you talk about modeling correlations, I mean, as I pointed out, Cox has this classical paper, 1981, where he talks about time series which can be categorized as observation or parameter-driven processes, namely whether you have the correlations on the observables over time, or there may be parameters, sometimes latent parameters, there may be a time series structure on those, and that's what he refers to as the parameter-driven type of structures. Now, when you model contemporary correlations, namely dependencies, I mean, there are certain strategies, but still modeling dependence is a very important problem in probability and statistics. So the famous paper by Marshall and Alkin talk about several strategies. One idea is obviously you can model by conditions. I mean, in fact, you can even specify all the conditions without specifying any marginals. And there is a very nice paper, I think, in the statistical science by Barry Arnold and his colleagues. So that's one way to do it, but then you don't necessarily have any analytical forms to be able to do analysis. You have to do everything numerically in that sense. Another idea is having a common environment type of model. So you can think that at a particular point in time, there is a random environment, and under that environment, you basically have correlations induced, and typically positive correlations as a result of it. I mean, this idea goes back to old days. There is a nice paper in Biometric by Arbus and Carriage where they use this idea for modeling accidents of different types, but it was not a time series. It was basically a static type of model. Schindler has some work on reliability in this context, and then Linley and Simperal had a 1986 paper on Journal of Applied Probability, which talks about this idea for inducing dependence on components of a system operating under a common environment. So that's the type of idea that we are going to basically take into account. So if you look at the previous work on multivariate time series of counts, I mean, there isn't that much work, but these are some of the highlights, especially in the recent times. There is a class of models which are known as integer AR models, especially Pedeli and Carles has a lot of work on this. I think they even had an application where they tried to predict the score of the soccer games as a time series. I think one of these papers is on that. You can talk about multivariate Poisson series using multivariate Poisson distributions, but multivariate Poisson even itself is a pain to compute because it involves all these sums and so on. And if you bring in any other correlation structure over time, things will still be cumbersome to be able to deal with. But you know, there is a nice paper by Ravi Shankar and our colleagues. And then there is another paper which uses some type of hierarchical base structure that appeared on the ASBE, the International Statistical Society's Business and Industrial Statistics section journal. Well, there are some state space model type of idea which goes to Ort, 1993. I mean, in fact, maybe some people may remember there was a univariate paper which appeared by Winkler, Ort, on the Journal of Business Economic Statistics, where they use some type of a state space type of structure. And there is a paper by Jorgensen along the lines. I mean, more recently, Mike West and his colleagues are working on multivariate time series, especially looking at data on the internet traffic, highly multivariate. So dimensions are high. So what they use an interesting idea, which they refer to as decouple-recouple. So namely, they start with a multivariate time series, bring in individuals, and then bring them together later on. And that in the bringing them together, there is some type of an evolution of a common environment as well. And what we are going to talk about is really along those lines. Okay? So here's the idea. So we have J. Yes, sir.
Well, somehow I don't see a thinning model approach because that's one of the ways people do.
What's that?
The thinning.
Mm-hmm.
So I didn't see anything about thinning in your.
But the thinning idea is sort of like this decouple recouple idea. In other words, you have the common, right? You thin, you split, and afterwards you can bring in sort of like that. I mean, they don't use that idea.
Right.
Yeah.
Because thinning can be done with the correlations between the components too.
That's right. That's right. No, you're absolutely right. But yeah, that idea is slightly, similar. But that's a good point. So here we have J different Poisson time series operating in a common environment. So this is the stochastic environment theta t. It's a latent, basically, variable. And then the lambda j's are the Poisson rates of each of the components. So one idea is you can think of it right. Well, there is a standard rate associated with each component of the time series, and there is a common environment. Again, this can be in economics. That's the common environment, and that induces some type of correlation. And then, depending on the scenario, as a result of the environment, things become harsher or milder, right? The rate can go up or go down depending on theta t is greater than 1 or less than 1. So that may be one way to interpret it. So the idea here is conditional on theta t and lambda j's and jt's are independent of each other at time t. So contemporaneously they are conditionally independent. Then similarly, conditional on theta t and lambda j's and jt's are also independent over time. So you have conditional independence in the contemporary as well as over time. And then, as I pointed out, this common environment, theta t, is a random environment, and that will bring or induce the dependent structure of these individual series. Okay? So again, this is an old idea, which goes back to 1950s. Okay, well, how do we deal with the evolution? Again, I mean, one of the ideas here is to obtain something as tractable as possible, so you can hopefully work in high dimensions. But for us, I guess, stat OR type of people, high dimensions really like 10, 12. It's not like what they talk about in machine learning, things like that. In fact, somebody once told me that there is a very famous statistician. The best statistical problem is small data set and a lot of science behind the problem. That's the best problem to study. Well, he's a Bayesian, so he thinks about bringing science into the analysis as well. Okay, so the idea is basically the following. The theta t follows a Markovian evolution. I mean, this idea again goes back to 1965. There is a very nice paper by John Bader on the Annals of Mathematical Statistics. Unfortunately, not very many people references him. And in fact, it's the title of the paper, I think, is the Invariant Conditional Distributions. And this idea was used by later others, Smith and Miller and Harvey and Fernandez. But you can look at it in two ways. One way to think about this is having a multiplicative sort of autoregressive structure, where theta t is related to theta t minus 1, and there is a coefficient which we refer to as discount coefficient. And epsilon t is sort of an error type of term, but it is a special structure in the following sense, because when we look at many AR processes, the epsilon t's are not related to the past history, right? Because you usually have yt as a function of the past errors, okay? But then the errors are not really related to the past history. In this model, you have this following assumption: epsilon t, given all the history of the data, namely in our case the counts as well as the individual coefficients, will have a beta distribution where the parameters are a weighted average based on this gamma, where alpha t minus 1 will bring in the history of the previous observations. Okay. I mean, alternatively, one can basically suppress this and specify a transition distribution as well, which will be automatically implied from the structure. Well, one thing to note again is the discount coefficient takes values between 0 and 1. So it also imposes some type of a stochastic ordering between these rates, the theta t and theta t minus 1. Okay? So in that sense, it provides some flexibility. Now, the model is quite tractable in the following sense. So if you look at a lot of these conditional type of distributions, again, everything is here conditional on the other lambdas, but also the discount factor. So you can show that this transition of theta, theta t minus 1, given all the previous data, follows a basically scale beta density. Okay, it's because of this particular structure. In other words, I couldn't even need to think about this. I could have just specified directly by specifying that transition density as well. And again, the model implies sort of like a random walk type of evolution. Expected value of theta t given theta t minus 1 everything will be theta t minus 1. And plus, if you start with the initial assumption that theta 0 given prior at time 0 as a gamma distribution, by induction you can show that the theta t minus 1 given the plasticity and all the other coefficients will have some type of a gamma updating as well. Okay? And in fact, this guy alpha t minus 1 is carrying, as well as the beta t minus 1, the effect of all the history in that sense. Now, when you look at the forecast distribution of the theta t, namely averaging out theta t minus 1, that happens to be another gamma distribution with the same parameters, which are discounted by the gamma coefficient. And it gives an intuitive structure in the following sense. You're saying that your forecast mean is the same as your filtering distribution mean at time t minus 1. But since you are looking one step ahead, the variance will be increasing. So that's the common assumption in these type of models, because you are looking at one step ahead, and that brings in additional uncertainty. And the common posterior density, namely at time t, when we go through the updating, namely from here, after observing the new vector of observations, will be a gamma, where the parameters will be updating in the following sense. Okay. And note that this is conditional on the lambdas, so you have this particular structure. So from here, we have a nice gamma type of structure, right, on the environment. Conditionally, the NJTs were Poissons, conditionally independent Poissons, right? So all the marginals, you can show it as some type of a dynamic negative binomial model. Okay? And the multivariate distribution, namely you write down conditional independent, integrate out the environment, right? Then you can show that it's a dynamic multivariate distribution of negative binomial type. So you can deal with over dispersion, you know, things like that. Now, in fact, this is nothing but a dynamic version of the bivariate negative binomial distribution of Argus and Carriage, which was used in 1951. So they have a static version. This was basically dynamic, which takes into account all the history of the things. Now, I mean, several properties, the regression of these type of models, conditional on the lambdas, are basically linear. Okay, they will be positively correlated. And the nice thing is, if you take different components, the correlation structure will be different. It depends on both the lambdas, the usual rates, or the corresponding components. So it has modeling flexibility. For example, this is not usually true for some other distributions, and I'll touch on that hopefully at the end.
Question?
Okay. Yeah.
Are lambdas assumed to be independent here?
When we'll put a prior on those, initially they will be independent, but as we are learning, they'll become dependent as well.
So across time, for example?
No.
Yeah, okay.
So in other words, yeah. I mean, you can prove, but then that will make things a little bit intractable, so that's one of the reasons.
So I was just wondering if you had started off with your model and where you assume lambda to be, say, for example, Markov, would that bring in more information about the transitions? Because in some sense here you're losing the transition correlation on a latent level.
Yeah, I mean, the alternative maybe can be the following. I guess you can assume lambdas are dynamic and then maybe have a static environment, right, which brings them. That may be another way of looking at it. That's true. Yeah, because now here jointly they bring that in. But yeah, that's I think that's a good idea, which can probably be tractable still. So here, yeah, obviously, as we just talked about, for a Bayesian, the lambdas will be treated as unknown quantities. We'll put some type of prior, and initially we'll assume that they are all independent. Okay, and then in the estimation, you can either use a Gibbs sampler. There is a full Gibbs sampler here, or as we will see, you can also use particle filtering with a particle learning type of twist. And then you can show that posteriori, conditional on the theta t's and everything else, the full conditions of lambdas are all gammas updated in the following manner. So they are pretty much similar to the updating of the theta t, but now all the theta t's will come into picture when you do the updating. Okay. So obviously they are unconditional, they will be dependent. But then when you do the draws in the Gibbs sampler, it's easy to do. Discount parameter gamma is obviously important. You can put some type of a beta distribution, a priori independent of lambda j's and everything. You can use a metropolis easily. Or in fact, you can even put a discrete prior with many, many points. In fact, that becomes more tractable when you talk about particle filtering. Okay. So how do you draw the thetas? Well, if you use a Gibbs sampler, you will, let's say, data from capital T periods on all these vectors. So you can update the theta 1 through theta t, namely their smoothing distribution, condition on all the static parameters, using a forward filtering, backward sampling, which is easy to basically implement here. And the way that it works, you first start with the posterior condition and everything at time t, then capital theta t minus 1 will be conditional on theta t. So that's the idea of the forward filtering. Okay? Because in our case, all these distributions will have some type of a shifted gamma form. So it's easy to choose. You can draw them as a block very, very easily by using the forward Monte Carlo. Using this one. Okay, now there are a few issues. I mean, if you try to use these things online, note that typically what the Gibbs sampler will do, it will give you the smoothing distributions. Namely, it will provide you with the distribution of theta 1 given all the data from periods 1 to capital T. So if you want to do it online, namely try to update things after observing data up to point t, then you would like to have distribution of theta t given dt, namely the filtering distributions. For that, you have to run the Gibbs sampler every time.
So in the computation, do you have to store those values for every time, or you just need to? Exactly.
Yeah. If you want to use the Gibbs sampler, then yeah, if I want to do it, I'll run it for 1 period, 2 period, t period each time. Exactly. Okay. Exactly. So that's one of the problems with using MCMC type of thing. And especially when you try to do, higher dimensional data, and if you want to real-time analysis, is computationally very costly. So one approach to use is particle filtering. I mean, it's a nice idea, but it's not always implementable. There are a lot of things should happen to be able to do it with less computation, namely to have something computationally efficient. But in this case, things will work, as I will show you. So what the idea of the particle filtering is, you don't really have the distributions, but you have the particles at each point in time, and when the data comes in, you update theta t to theta t plus 1 particles. Okay? So it's really like, discretized type of things. But then the idea here is when you update from theta t to theta t plus 1, when the new observation comes in, you would like to carry those theta t, which is supported by the data mostly, right? Because otherwise, you can basically get into what people refer to as degeneracies. You can only carry very few particles from time t to time t plus 1 as a result of evolution. So that's one of the things one has to deal with that. So typically, what we want to do is we update things at time t based on data from 1 to t, then a new vector of counts becomes available, and I have to basically update to theta t plus 1 using this in a efficient manner. Okay. And that's the idea in the particle filtering. Well, there are few issues. Particle filtering usually is not designed for updating static parameters. I mean, the idea goes back to early days. People have been using this, but typically they always dealt with dynamic parameters. So we have here, depending on the dimension, capital J static parameters, and we have to update them without rerunning things every time. And this can be done if you have certain conditional sufficient statistics available. And this idea goes back to Storvik. I think it's 2001 or 2002 paper. And he basically shows that, yeah, if you have sufficient statistics conditional on theta t's for the lambdas, you can do this updating without rerunning everything. Okay. And it's possible to do that. This is usually what sometimes people call particle learning. And there is a very nice paper by Carlos Carvalho, Michael Johannes, and Hegibert Lopez and Nick Poisson, statistical science, which talks about doing particle filtering with the static parameters. The implementation of this requires two things. One is the availability of the predictive density of the new vector of counts given the previous value of the state and everything else, including the static parameters. And then you need a propagation density, which is different than the usual one that we use. It's the distribution of theta t plus 1 given theta t static parameters. Typical one involves dt, but this involves the new vector of observations included in the dt, which becomes dt plus 1. If these are not available in tractable forms, it's very difficult to implement the particle filtering idea. Okay. So let's see. So I have about 15 minutes.
20.
20. Okay. So the idea of the particle filtering with the particle learning is the following. So what you want to do, you updating things at time t, right? Then a new vector of counts comes in. Now what I want to do, I don't want to use the old values of theta t based on the information available up and including the time t vector. So I want to also borrow strength from the new vector of counts. So that's why I want to first update theta t's given the new vector of counts. So that's really like a smoothing type of idea. So from the filtering, we first go to smoothing, update the theta t's, and then use those theta t's for the evolution. That basically is shown as dealing with this degeneracy problem. So that way you are not basically carrying those bad theta t's, which are not supported by the new data. You are only carrying those, namely they are given high probabilities, supported by the new data. So I can use the evolution of the theta t plus 1 based on that. Because if you look at the usual structures, the thing which was typically done, you have the distribution of theta t's based on what you observe. You first propagate, update theta t plus 1. That will be like the prior distribution. Then based on the new information, you update the state vector at time t plus 1. Okay, but then that uses whatever theta t's that you have from the previous one. Some of them may not have the support of the new data, right? So that's why availability of this guy is important, because it will enable us to update the theta t's given this one. So this is really like a smoothing likelihood for theta t in that sense. Okay. So here's the algorithm. I'm not going to go into details because that summarizes the idea that I talked about. But what I do first, once I have the analysis done at time t, I have the posterior distribution, everything. Now the goal is I'm going to somehow resample new theta t's using the information from the new set of counts. Then I'm going to propagate to theta t plus 1 and update that distribution. Then, since I have a sufficient conditional statistic of the lambdas, I will go and update lambdas by just updating the sufficient statistic. And after that, I'll basically draw those and then go to the new iteration. So that's, yeah.
Is there any reason for not changing the number of particles as it goes through the propagation? Because I would expect that as you go further in time, you are not going to get...
Well, the thing is, yeah, because since you do, like in discretely, right, you have k values from the previous part, right, and then you carry, so the idea is you start with a larger number of particles, and some of them may die on the way.
Right, that's why I would keep adding more particles so that I have more information at the later generation. But then,
yeah, but then what you will be doing for the same value of theta t, let's say particle, I'll will have replications.
Right.
That can be done in that sense. Yeah.
Okay.
Yeah. Yeah. In fact, that way, that's usually one way to deal with if you lose. I mean, if
right, because you may die out.
Yeah, exactly.
Exactly. Yeah.
I mean, that's when they, because usually what people do, they will first in the particle filtering propagate and resample. I think Vadim, in your paper with Nick on the traffic flow, you use that, right? Yeah. I mean, in those type of situations, that may be also a way of dealing with degeneracy to have more applications. Okay, so then the sufficient statistics are really coming from the conditional distribution of lambda given all the theta t's. So at every iteration, the only thing that I have to have the previous value of the sufficient statistic, the new observations, okay? So this is the vector, so I just now wrote everything with yt's, and then update it that way, okay? But the key thing, for all this to work, you need the distribution of yt plus 1 given theta t and everything else, as well as the distribution of theta t plus 1 given theta t and dt plus 1. So in this case, those distributions happen to be available. In fact, the first one, the predictive likelihood, so this is really like related to sufficient statistic, but it's equal to this guy. So that's the distribution of the vector of counts. So that's what the y denotes here, given theta t lambda dt, which can be easily obtained. You can show that. Now note that this distribution, we are not sampling from that. We only need to evaluate it. So each value of theta for the given value of the new vector of counts. And then we use it as a weight to resample the good theta t's using the posterior distribution. That happens to have a distribution which is related to confluent hypergeometric functions. Well, they can be computed, even there are ways of computing them. So we refer to this as the dynamic multivariate confluent hypergeometric negative binomial distribution. But it is a long name. Okay? So that's the first one. The second one, the other type of propagation density, namely the one which depends on the previous data as well as the new count, that can be obtained as a scaled hypergeometric beta density. This one I need to draw, because once I have the new theta t's weighted by the new vector of counts, I'm going to generate from this distribution. Sometimes it can be pain, but this is only one dimension, so rejection sampling works very fine here. You can basically find a nice density to cover this. But if it, for example, if you have high dimensional theta t's, like your initial suggestions, I'm not sure how this will work. Okay, then we have to update the discount factor. So in doing that, we are using a discrete prior, because in the particle learning it works easily. And the idea is the following. Given the lambdas, I can have the conditional posterior of gamma, the discount factor, based on a discrete prior, because this distribution is available. And I can basically generate a lot of points. And then I can do a Monte Carlo average with respect to the posterior of lambda to get the posterior distribution. So that's the way it is done. Okay. Well, the obviously reasonable question, how does this work? Well, it works when you have strong correlation. Right? I mean, intuitively, this type of model, which is a coupled model, makes sense only have positive correlation, and there will be some correlation, right? Which is brought in by the common environment. Otherwise, you don't want to do them as a multivariate. You can decouple them and run them separately. So we did some first simulated data. So dimension 5. So these are the lambdas that we chose, simulated. And then we have two cases, low correlation. Correlation is about 0.3. And obviously here, the legitimate question is when you deal with time series data, even computing correlation is not straightforward, right? And high correlation case, we have generated things in the range of 0.8, 0.9 because we have multiple replications to show how things work. And then we work in this case with a gamma of 0.3, which also implies a smaller gamma implies higher correlation in that sense. And then these are the values that we use.
Would it work equally well if you had all the lambdas equal?
But if you have all the lambdas are equal, then you have really like a one-time series, right?
Right.
Yeah. So you want to separate them out at least in that sense. And then we just generate, I think, 120. But for the high correlation case, we ran 10 replications. In fact, in the study, in the paper, there are some details on some type of benchmarking. So this is the case for the low correlation. Well, these are maybe not very well seen, but the dark one here, for example, is the original data. This is the fit, not very good, right? And then the green is the fit, the other one is the actual data. So when you have low correlation, things do not seem to be working very well. But if you have high correlation, yeah, if the correlation is 0.8, 0.9, they work very, very good. Intuitively, you're saying that now you borrow strength from the other time series, right? So you have a situation like this, and then the model captures that.
So
yeah.
In the low correlation case, you would like to believe that they are like replications, in which case you would expect an improved performance. So there is something that we are missing here, right?
Yeah, I mean, one idea of that, you can bring in covariance is maybe possible.
I see.
Yeah, yeah, exactly. I mean, in fact, the example that I show you is not that good because it has a low correlation with real data. That's the case. But here, if you look at the study, I mean, note that the first should be actual value was 2, so these were all the posterior credibility intervals with the means. For example, it can go as low as 1.7, 1.6. But in most cases, about, in the correct region, even the mean, so you have the coverage and so on. So for the high correlation case, everything works pretty well. Now, this is actual data. These are weekly grocery store visits of Chicago. What if this has nothing to do with Nick is in Chicago, but data happens to be that way. And we took, this is over 104 weeks. We just took only 2 households because the reason for that, most of this data was not very highly correlated. The highest correlation was about 0.4, 0.5. So this one, these 2 households is giving that correlation. And then we are basically assuming that we have the common economic environment, so that will probably, will change the number of trips that you make to the grocery store. Okay, so that's the, yeah.
No vacation. In other words,
well, I guess in this case,
from where you don't go to the grocery store because you're in the hospital.
That's true, yeah. Well, I'm not sure. Yeah, that may be possible. I mean, we don't have that type of data. Yeah, here we only have the number of shopping trips, but these are like number of weekly trips, right?
I was wondering whether you needed something like a modified Poisson where the zeros can be.
Yeah, probably you can take that into account, but I mean that's not the purpose here. We just want to, yeah.
But vacation is going to be correlated as well, right?
Mm-hmm.
So people more likely to go in August than in January.
Oh yeah.
Yeah, but I mean that's why I think goes back.
Complications.
Yeah.
But you can bring in covariates and all that. I mean that's potentially there, but I'll talk about it. It will create some problems depending on how you want to do it.
Do you have a plot of some autocorrelations in your simulated data?
We may have some of them in the, but most of these autocorrelations, I think, they were pretty much lag 1, lag 2, and it disappeared. So the first order Markovian was not that bad, if that's the, yeah, exactly. So in other words, when you look at the individual series, there is, correlation. But when I'm talking about correlation between the series, is not that high, about 0.4. So these are the two series. I mean, not that they are, most of the time working in the same direction, but there are places where they are working in different directions, right? So the correlation is not really that high over time. And then, so here, the blacks are the actuals, the reds are the predictions based on the means, and then these are the intervals for the series 1, series 2. Obviously, these are predictions based on the bivariate model. Now, they do better than if you decouple them. So still, I mean, it's not obviously perfect because there are a lot of things which we don't even capture, right, at the beginning in the intervals. But after you learn more, things get better over time. But this still does better than if you run them separately using the Markovian evolution the way that we brought in, but don't have any connection between the two series.
I have a feeling maybe there is a time trend that's present in your data does not capture.
Yeah, T is in weeks.
Yeah, T's in weeks. I mean, there are a lot of factors we don't take into account, but there isn't that obvious time trend, but there may be seasonalities, right?
Sorry.
Exactly. So that I mean, seasonal type of trends, obviously.
Yeah, in some seasons you may have.
Yeah, exactly. Yeah.
Right.
So I mean, that may be the reason. So obviously, one can bring those in, but I'll touch on those. And then these are basically posterior distribution of lambda 1, lambda 2. So one family, without the effect of the environment, has a tendency to go more than the other one. That's basically what it implies. And then you can, this is also the behavior of the random environment. So that sort of tries to pick up, obviously, the patterns that you have in the data. But note that it's sort of like the two series mixed together, right? I mean, that type of updating that you will see here. Okay, now, one thing which is possible to do, I'm not going to get into details, but you can take this idea and generalize it with other non-Gaussian type of series. So this is a quite general form, and have the same type of evolution. And depending on the underlying model that you have, where you have the conditional independence assumed, you will have other parameters as well. Okay, for example, I mean, the thing is then, when you look at the joint distribution after averaging out the environment, remember I said it in the Poisson case, you got a multivariate dynamic version of negative binomials, right? So here, for example, you can obtain a multivariate Lomax or multivariate general and Lomax, depending on whether you have exponential time series, gamma time series, or Weibull time series. You can have dynamic versions of lot of the well-known multivariate distributions using this idea. So it's quite straightforward in the gamma. You can basically do that. So there is potential to apply this to other type of models as well.
And make each of the y's have a common type of distribution as opposed to having different distributions.
No, everybody has a common type of, yeah, exactly.
Yeah,
exactly.
Because if you wanted to have the series that had the cost, what the expenditure
yeah.
as well as the number of trips.
But that type of dependencies, I mean, because at the end of the day, you'll have a multivariate distribution, right, at a given point in time. If you have different type of distributions, the only way to do that is by specifying conditions, right?
Right.
And that's difficult. I mean, we probabilists and statisticians, we don't really know much about how to model dependence, right? I mean, that's probably the most important problem. There are few ideas, right?
But you can map it back into a common
In there,
distribution.
yeah. But you can, but then you also want to have something tractable. That's the idea. We want to compute things at the end of the day. Right? So, couple of ideas. As I pointed out, this setup can be generalized, and it can capture members of generalized gamma and time transformed exponential families, the type of time series. And still, the particle filtering methods can be developed with the caveat that some of these other parameters, I denote as new, they are really nuisance parameters, and they are really nuisance to learn because you want to have sufficient statistics, conditional sufficient statistics for many of them. I mean, for example, estimating shape parameter in a gamma distribution is not straightforward. So you have to deal with that. But the generality of the results, you get always propagation density as some type of scaled hypergeometric beta that still be applicable. And those resampling weights, remember that predictive type of density or the smoothing likelihood, if you want to call it that way, will have some type of a multivariate confluent hypergeometric distribution. So you have to know how to generate from those. Now, it is possible to include time and component dependent covariates. So for example, if you take the case that we have, so you can take the lambda j and put some type of a Cox type of model on there. But if you do that, all these tractability will be lost. You have to use basically Markov chain Monte Carlo. Okay, so you cannot use particle filtering because there won't be any conditional sufficient statistics to update the static parameters. But you can use MCMC with a mixture of Gibbs and Metropolis steps in between. In fact, one of the papers that we have in the Annals of Applied Statistics, we use that idea for the mortgage defaults. It is possible, but it is costly if you want to use particle filtering. And we have a paper on that which we got rejected and resubmit. I guess it's one of the good stories, one of the good stories these days, which talks about this. We call this as the dynamic transformed exponential family of multivariate models. And I think that's all I have.
We have time for questions.
I have one slightly different philosophical question. While these models are very driven by certain aspects, they are not mechanistic in nature, in the sense that they do not tell us that this is what leads to this and so on. So if we had, for example, some idea about the marketing, how this might work, or in the hospital data, if you know how the arrivals, then those can be brought in a more interesting mechanistically. And that can potentially, then one could use these models or thinning type models where you can allow thinning parameters to depend. dynamically and change, and that can produce potentially a more interesting solution. That's just a
probably. No, that I think tuning idea is a good. In fact, this our idea of the decouple, recouple, I think is an intelligent way to do it, especially with very high dimensional data. I think there is definitely potential in that.
Yeah, what you're saying, what do you really learn from all of this procedure? Is that another way of putting what you're saying? Or
well,
maybe not.
Anyway,
I
don't want to. There are things you learn, but I'm saying there may be some more information that could be extracted if we pursue a mechanistic approach on bringing in additional information about the market trend, for example, and then saying that how do people move, and there are some differential equations that determine those. And in that case, then that can be brought into the picture through the mechanistic model, like a thinning type models, which involves parameters which are dynamic. Okay. And then we can, in that case, the sequential Monte Carlo becomes the tool because your dynamic parameters are dynamic.
Yeah, I mean, in fact, the paper by Vadim and Nick on the traffic flows, network traffic flows, it basically starts with science. So you have basically a model of differential equations, right?
Stochastic.
Yeah. So from that, yeah, exactly. I think that maybe, especially if you have, some type of engineering problems where you have some type of time series, yeah, you can start with that. That will obviously add to the model, no doubt.
Any other questions?
Are these slides available for our use?
Sure, you can make them available.
Yeah, sure. We don't have a website for our seminar series, so you have to email me, and I'll email you back.
Well, I know there was an invitation sent out for this event. Can you use the same distribution?
Well, maybe not everybody wants these slides.
Yeah.
Well, they don't have to. They can just click on the link if they wish it.
If I don't send it, just send me an email.
I will send you an email. Or I'll give you my card. So.
I actually have a question.
Yes.
So you have. I'm sorry.
Go ahead. I was going to say you're dealing with counts, and there are related times to these count events or whatever, like how long it is between shopping trips. So have you looked at the relationship between?
Yeah, I mean, another thing that I was, for example, instead of looking at in that data, maybe the count trips, you can basically look at the time between the first trip, second trip, and that can be your temporal data, time series data. And then you can try to model that by a multivariate duration model. That's possible.
But then you might want to know how much the expenditure was, or how much the distance to the function was.
Yeah, I mean,
In those things.
you can always bring in other things.
Right. Definitely. Go ahead, sorry.
So in your original setup, when you have your data is Poisson distributed and you have theta times lambda, it's a product, right? So can you have a more general type of model inside your Poisson? So instead of product, even some linear model or even some generalized linear model inside. So more general way to incorporate dependency on the common environment than just multiplicative.
Sure.
Well,
Well, but yeah, I mean, even if you go to GLM type of stuff, you really do multiplicator, right? You take the log and it's linear.
Right.
So,
yeah. But linear will work. The same. You try to be.
well, but then you have to put certain conditions, right, on the.
Okay.
Yeah. Well, because I mean, here it works because the product of those distributions give you a gamma, right? I mean, there is a conjugacy structure that you want to. The idea is the simplicity, right?
Okay. Any other questions? Let's thank Refik again.
Thank you.
Thank you.
Thank you.